Okay, is this on? Okay, yeah, so we're good. Amazing. Oh, it's so nice to see such a big turnout here at the center of the universe. So nice seeing so many people wanting to learn about science and astronomy, and especially about black holes, because they're so cool and they're kind of creepy, and I think that's why everybody loves them so much. So welcome to a mostly safe guide to black holes. So today what we're going to do is we're going to have a little bit of a conceptual understanding of what they are. We're going to look through what makes up a black hole, what happens when things interact with them, and then what we're going to do is we're going to go through an actual simulation of us falling into a black hole together. And then I'll tell you exactly what would happen to us and what would happen, what our friends would see, what would happen to us. And it's different. Black holes are full of paradoxes, but that makes them way more fun to talk about. But before we start, we got some rules. We are not responsible for any feelings of existential crisis, time dilation, or spontaneous ponderings of your cosmic insignificance. Side effects may include vertigo, awe, confusion, and sudden respect for Einstein and Hawking. And if you start hearing any whispers from the void, please contact your nearest astrophysicist. Okay, so we got that out of the way. We can begin. All right, so the first thing we need to understand about black holes and about space is that they act differently than we normally would think about space. We think about space as being completely empty, and things are just floating through this blackness of this void, right? But actually, space is what we call it the fabric of space, or space-time. So we understand space, like our general space is like in and out, up, down, left, right. And then we also understand time. Time always travels in one direction, or so we think currently. Space-time puts those together, and you kind of get like a grid as to what space actually looks like. And so if you took this grid and you placed an infinite mass on them, or a source of infinite gravity, you're going to have this sloping kind of geometry. And that's the big thing. Black holes are not an object. They're a geometry. They are a figment of what happens to space-time when you place something with infinite gravity in one spot. And so black holes, one thing also, they don't suck things in. They're not vacuums. Things just fall into them. So if you get a little bit too close where it's not safe, you can fall in. But if we pretend that we substitute a black hole for our sun, so a black hole the exact same mass as our sun, and we just place it in there, nothing would happen to us. I mean, we'd have no light. We'd also probably die. But like nothing would happen to any of the planets around us. They'd go in the same orbit as they would have before. So they don't suck things in. Things just fall in. And so this is a bit of an example of what would happen if you place things of different mass in your fabric of space-time. So your Earth is, honestly, the mass of the Earth is negligible. It's so tiny compared to everything else in space. But if you even add the mass of our sun, that divot gets a little bigger. You add a black hole, and now that divot is infinite. The best way I like to think about it is the fabric of space-time is like a piece of black stretchy fabric. You and 4 friends are now holding your piece of black stretchy fabric at 4 corners, and you have another friend who comes in, places objects of different mass in the center of it. And as these objects get bigger and bigger, that divot increases. And that's exactly how things work in space. And that's how gravity works. Gravity is not technically a force. It is just what happens when things kind of fall into these ridges around objects of great mass, around space-time and things like that. All right, so there is a theory also to kind of help you wrap your head around it. It's called the river theory. So if we pretend space-time is like a river flowing through space, and our black hole is a cliff, a waterfall, a hole in the ground, and we are a fish. Let's call it a salmon. Since we're on Vancouver Island, we are a salmon flowing through this river. And our salmon is a photon, okay? It's light. And so as this river travels through space, it starts to fall in or fall off our waterfall, fall into a black hole. And we are light. We can go as fast as light, and nothing can go faster than us, right? And as we fall off the cliff, there's actually a weird thing that happens where you are suddenly going faster than the speed of light. And so you are now a fish trying to get up the rapids, up this waterfall, and you can never get out. You've passed what we call the event horizon of a black hole. You are stuck there forever. There is no returning from that portion of a black hole. So we're going to go through a little bit of a geometry, pretend this is an actual black hole. There's three main parts of it. One is the accretion disk. So this is the piece that we can actually see when we look at black holes with telescopes. And I'll show you photos that we had taken with these telescopes, and you'll be able to see the accretion disks of them. These are usually incredibly large disks of gas, dust, of poor stars that got a little bit too close and got shredded apart, and now they're forced to orbit around this black hole. And so that's the accretion disk. And then you get to what we call the event horizon. So now that is the point of no return. Nothing can escape, not even light. So that is why they're black holes. You literally cannot see in them. There is no light emitting from them anymore. And then the true monster of the black hole is that singularity. So that singularity is that point of infinite gravity, and it is the point where time ceases to exist. There is no time in a black hole, which is also really hard to wrap your head around. The time just changes. And when we go through the simulation, you'll also be able, there will be a little counter over here on this side of the screen, where you will be able to see the time that you experience as you fall into a black hole, while also comparing it to the time that your friends experience as they watch you fall into a black hole. And you'll be able to see the change that time takes as you get closer and closer to this point of infinite gravity. All right, so black holes can come in all shapes and sizes. You can get really big king-size black holes, or little fun-size black holes is what I like to call them. And so we're going to go through what some of these look like. So this specifically is like cutting research. This is kind of like just happening. So it can absolutely change. So these are what we call little red dots, because they look like little red dots. And astronomers looking up at the night sky were finding these things everywhere. And we looked at them and we started to study them, and around 70% of these little red dots, we found that they have an accretion disk around them going around 1,200 kilometers per second. And we've only ever seen those around current supermassive black holes. And so there's one more thing I need to point out. Each of these objects has a Z number associated to it, and that is what we call cosmic redshift. So these objects are super far away, like beginning of the universe super far away, at least as far as we can possibly see. The higher the Z constant, the further that light has had to travel. Therefore, your light has lost a lot of energy. It's super tired now that it's hit us, and it's more red. And so that's why we call it red shift. So we think these are actually some of the first black holes that ever formed in our universe. And so again, it's not truly proven yet. It's always changing, so don't come after me if I'm wrong. But this is like what we think supermassive black holes come from, because believe it or not, we actually have no idea where they come from. We know where stellar mass black holes come from, these guys. So this is what we think of when a really big star explodes. All right, so a star much bigger than the sun. Our sun will never turn into a black hole. I'm promising you this right now. But these stars, as they get so big, they're actually, all stars are kind of going through what we call like a balancing act throughout their entire lives. There's so much mass in them that's constantly wanting to push down, of course, with gravity. Gravity's always trying to pull things to a center point. And so a star has to create energy, right? It has to fuse hydrogen into helium energy, and that's how we get heat and light. And so it's like a balancing act of pressure going up and pressure going down. And then as stars come to the very end of their life, it's run out of that stuff to make it glow, to make heat, to keep it alive. And now all of a sudden, all of this mass is coming and crashing down really fast. To a point, it's about half a second from the time a star collapses to when it's a black hole. And so stars don't always turn into black holes. Sometimes they go supernovae, and then you get left like remnants of like a white dwarf or a neutron star or magnetars or some of these crazy things. But a lot of times they do turn into black holes. And what's creepy about them is because you can't see them. And the only time you can see them is when they interact with things around them. And so we'll talk a little bit about how black holes do something called gravitational lensing. And you can kind of even see it here in the image where the stars around them look super distorted. And then we'll talk about the really big guys. So these are supermassive black holes. Now this is an actual image of our black hole, Sagittarius A star, at the center of the Milky Way galaxy. We have actually looked at two black holes with a giant telescope. So what I'm going to talk about first is how we found our black hole, because we actually had no idea that we even had one until about 2002. And so this is an image taken, so we'll see t equals 0 here, and t equals 39. So this has been taken over about 40 days-ish. And so where this circle is we were looking at this area. The first evidence that we had where these stars were going in this really weird orbit. They were like whipping around in all weird areas, and we're like, what is here that is making these stars do this? So we stared and stared, and then they found a really, really bright radio source coming from the center. And they're like, oh, something is there. We have a supermassive black hole at the center of our galaxy. Therefore, now the ball is rolling into black hole research for us. So here's another image of ours. So this is a polarized light. So black holes have a really, really, really big magnetic field. Earth's magnetic field keeps us safe from solar flares and things like that. That's how we get our really pretty auroras. But a black hole's magnetic field is in like magnitude stronger. Like nothing like electrical will work around this thing. Everything's broken. And this is an image from the Chandra X-ray telescope. So this is a space telescope. It's not a ground telescope. And this is looking at a black hole in the galaxy M87. This is a very, very large black hole. But do you see how big this accretion disk is? That's all that orange stuff around it. And that little itty-bitty spot of blackness is the actual black hole. So the accretion disks of these things are gigantic, which makes them super interesting to study too, because what even made them? There's maybe stars that got a little bit too close, maybe huge dust clouds that have come down, and now they're spinning around this black hole. And these accretion disks go fast. Remember, like 1,200 kilometers per second and faster. So what we used was called the Event Horizon Telescope. So now this was like crazy. They made a telescope the size of our planet. So they used radio telescopes all the way from the Arctic down to the Antarctic to stare at black holes all the time. Even like if it was night on one day, it's a day on the other side. So they're constantly looking at these black holes. And so the first one they looked at was M87, that X-ray one I showed you, because it's so big. And then once they took an image of it, they're like, all right, let's look at ours. And then we were able to take an image of ours. And so this is interesting. So this in the middle here is what we computerized. This is completely generated in the middle of what we thought a black hole looked like. This is the actual image of it. And this is this like generated thing on the side is just blurred. And so we were like almost spot on of what we thought a black hole actually looked like. And it was crazy. Everyone was so excited when we got the first picture of a black hole because all of them are right. It looked the exact same way that we thought it was supposed to look like. And so this is like the true image. So this is Sagittarius A star. All right, that little dot in the middle is our sun. So it is still very large. Okay, this black hole is about 4.5 million times the mass of our sun. It's a big one, but technically it's actually considered a smaller black hole because this is the black hole in the middle of M87. Our entire solar system can fit within the actual black hole itself. This black hole weighs about 6 billion solar masses. And most black holes are usually this big or bigger. So they're literal monsters in the middle of galaxies. And that's why we think galaxies also get so big. Because we don't know how these guys form. We don't know. We think maybe it's mergers of smaller black holes to get into bigger ones. Maybe it's really big clouds of gas and dust that collapse in on itself from gravity, and that's how we get black holes. So we actually have no idea, which is cool, because there's so much to learn out there in astronomy, because we actually really know nothing, even about black holes. So the idea of how they get so big. So this is a computer simulation of something that happened. This is a black hole merger. So both of these black holes are about 30 stellar masses. So these are stellar mass black holes, not supermassive black holes. And this is like the dance that they do as they start to merge. And there's a very special interferometer, or a special kind of telescope called LIGO that measures when this happens. This was the first like stellar black hole merger that we had ever recorded. And so when they merge, you can see how it's distorting all the space-time around it. And then finally, when they come together, they send ripples through space-time. So think of just dropping a rock in a lake. All of the ripples of the waves that come out is how we can record when a black hole mergers. And that is exactly what we found. And I think we found another one, like last week, of a couple black holes merging as well. So we're always looking, and these guys are always active in doing things. And this is the other one I want to talk about, gravitational lensing. And so this is going to play over and over so you can watch it. But this is what happens when a black hole passes in front of things. So remember, they are distorting all of the space-time around them. So light curves around them on the sides, it curves around them over top and underneath. And so this is really useful because we can see things we never would have seen without a black hole lensing all this light. Because it's literally pulling the light towards us, kind of like this animation. If you pretend my little bird here is a black hole, all the light coming from, let's say, a star behind it is getting curved around it and it's coming to our eye. Otherwise, we probably wouldn't have seen it in the first place. And so black holes are super cool, but they also kind of open a door into us being able to see more and more of our own universe and understanding how we even got here in the first place. All right, so black holes aren't necessarily always alone. All right, sometimes you find an apple or piece of gas or stars or a sock that you may have lost. But black holes are not always lonely. Sometimes they're found with friends. So sometimes they have what we call like a stellar mass star. So the same kind of size as our sun can be found around black holes. You can have an even bigger size sun. So think of Betelgeuse. Huge star can be found around black holes. And what's interesting is, let's say you have a star this big, got a little bit too close to this black hole. That black hole will siphon the entire atmosphere off of this giant star. And you're left with the itty-bitty white dwarf, or the core of that star that is left that will continue to orbit around this black hole until it too maybe gets a little bit too close if its orbit is not stable. And then you can get to that kind of kooky weird things like magnetars and neutrons, pulsars that also go around the black hole. Aren't they cute? They're from NASA. I love them. So yes, black holes are usually found with some other thing as well, especially stellar mass ones. Supermassive black holes, of course, they have an entire galaxy around them. But stellar mass ones, you can find other objects also orbiting around them. And so before we go into the simulation, it's important to know where you would be safe around a black hole and where is not safe around a black hole. All right, so remember, if we have replaced our sun with a black hole on Earth, we're technically safe. But you're not safe in the black hole or the accretion disk, or these are quasars. These are jets of like crazy X-rays that come off of the black holes if they eat a little bit too much. But there are spaces you would technically be safe if you're trying to orbit around a black hole. And so we can see that when it zooms out in a second here. Yeah, not safe in the actual black hole, and then super safe around it. All right. So when we go through our simulation, pretend this is where our spaceship is docking, and we're going to be in the not so safe spots as we kind of leave that spaceship in like a little probe and head into this black hole. And so we have our safety card. We are now this traveler. We are getting in our rocket ship. All right, and we are going to blast off towards a black hole. All right, so are we all ready? Perfect. So remember, this is an actual simulation of us going into Sagittarius A star. We are now in our rocket ship flying towards this black hole. And when it pauses, that is where we are leaving our friends behind in their spaceship, and we are getting into our own probe, and we are going to fly into the black hole. And so this next slide, I'm changing it up a little bit. We are going to have the same kind of vision as a camera falling into this black hole, and it'll give you a really good idea how fast we're going, what time is doing, and what it looks like to see all that light bending around us. All right, so you can see time here, and you can see camera time versus external time. External time is the time our friends are experiencing. Camera time is us. And our trajectory is right here. And so it is going to slow down just because we're going so fast, just to give you an idea of what it's like to fall into one. And so as we get faster and faster, the light is bending around us as we're falling into the black hole. Remember, we're not getting sucked in. And the light in front of you is also going so fast. It's brighter in front of you than it is going to be on the sides. And so we're slowly falling. We're like in the midst of the accretion disk. Just a moment before we actually hit the event horizon. So we'll hit the event horizon now, and you'll notice the universe above your head is going to start to fade away as the light from the accretion disk also will start to fade away. And you fall into the blackness of nothing. And so, as your friends watch you go through this, once you hit the event horizon, they actually just watch you fade away. They don't actually see you fall in, technically. The light from your body that's reflecting off of you to go towards their eyes is getting sucked into that black hole with you. And so they just see you kind of disappear from existence. But now it gets a little crazy, because now enter Stephen Hawking. So Hawking kind of broke physics. So there was a long time, we thought black holes, we think they still kind of do, that they destroy information. And that's, every physicist is like, no, energy cannot be destroyed. But we thought black holes did. And that didn't sit well with Hawking. And so the vacuum of space isn't actually empty. There are, particles, and there's photons, and there's sometimes what you get virtual particles. And these are positive and negative particles that just appear, and then they collide, and then they disappear, because they cancel each other out. And so we think that there are virtual particles that can appear around the event horizon of a black hole. And this is what we call Hawking radiation. And this way, your black hole is technically emitting something. And what we see it as is like energy or heat, really. We call it a black body for any astronomers in the crowd. And that's also what the sun is. You can measure it as a black body. It's giving off heat. It's giving off radiation. You can actually measure that. And so now, pretend our friends that are still in that spaceship before we rewatch the simulation are throwing in a thermometer as you are flying down in your probe. And on that thermometer, because of Hawking radiation, the temperatures read around that black hole are excruciating. There's no way we should survive that. And so we're going to go through this simulation one more time. We had Alan turn the lights off to make it even more fun. Amazing. All right. I'm going to walk us through it a little bit, all right? So, remember, we're flying in our spaceship with our friends. We're going to get to a safe point just before the accretion disk. Probably right about now-ish, all right? We disembark from the spaceship. We're in our probe. We're now flying towards this black hole. We are now in the actual accretion disk of it. We're circling in, going faster and faster and faster as we head towards that event horizon. And as we get so close, our friends are now seeing us being incinerated. We have been incinerated according to them, but for us in this room, pretend this is our probe, we don't know anything's actually happened to us. We just feel as if time is still going. But the moment we cross that event horizon and we head closer to the singularity, and the geometry of the black hole gets narrower and narrower, what we experience is something called spaghettification. Because remember that singularity is a point of infinite gravity. If we're heading in and we're feet first, the gravity at your feet is stronger than the gravity at your head. So the black hole is going to rip you apart to your molecules, and then it's going to rip you apart to your atoms, and then it'll rip your atoms apart into the protons and electrons and the neutrons, and then it'll rip those apart into the quarks that make them, and then it'll rip those apart into the actual intrinsic energy that makes up anything into our universe. And that's what we think maybe gets erased in these black holes, so you just cease to exist, as does time. It is truly a sense of nothing at a singularity of a black hole. And so, congratulations, you've technically come out unscathed from entering a black hole. But as we end this presentation, I truly hope you're leaving with more questions than when you came in. Because I want you to go out and look up at the night sky and truly understand that we are nothing compared to everything out there. And there's still so much to learn, so much science to still be done, to not just understand things out there, but to understand where we came from, where our galaxy came from, our solar system, the molecules in our body and the atoms came from. So there's way more to black holes than them just kind of sucking things in. Remember, they're not actually sucking, but pretend. Things are falling in. They can truly unlock some of the secrets of our universe the more and more we study them. Thank you. Okay. I think there's time for questions. Oh, wow. Yeah, okay.
How do you get to infinite gravity? Like what?
How does it even get, yeah. So when you're thinking about, let's take an atom, right? And the space between the nucleus of an atom and an electron is still huge. There's actually so much space. And so when you have things crashing down on each other, these electrons are trying to find a space where they can be on their own and not smooshed up with the nucleus of an atom. And so the more and more you do that, the less space you get, and you get to a point of infinite gravity. I truly don't understand how it happens. If I did, I would have a Nobel Prize in physics. But yeah, it's kind of crazy. All right, any other, ooh, yeah.
Those red dots, that would probably be the black holes thousands of years back in time.
You are absolutely correct.
It takes so long for light to travel to our eyes because they're so far away.
100%. We think those are black holes billions of light years away. Well done. All right. Any others? Are we good? Yeah.
So there is that concept of the most reliable source of information, internet, right? That our universe is inside of a black hole.
Oh yeah, that's a classic one. Yeah.
I don't want to ask if that's true. What make us believe that theory?
All right. So the question was, there is a theory that our entire universe exists within a black hole. And I just told you black holes destroy information, or so we kind of think. But Hawking radiation, there's an aspect of it that the information sits right on the surface of it. And so what we think of something being full of information, you can think of it like a library, right? The more information you have in the library, the more books you can put in the room. For a black hole, the information that we think survives is like if you actually take the pages of the book and you cover the the surface area of your library, and that's where all the information lives. So it's not information that you can take and put things back together, right? It's like burning a piece of paper. It's gone. You can't actually put that back. There's energy that's been released. But we think there's that intrinsic information that we can somewhat measure, and that's that kind of heat that comes off. All right, let's do one more. Yeah?
What happens if you put electronics in a black hole?
Let's say you try to throw a computer into a black hole. Same exact thing that would happen to us would happen to that computer. One, it wouldn't even work. The magnetic fields of this black hole are way too strong, so your computer wouldn't even turn on, but your computer would get torn apart into its atoms, into its energy at the end. So anything that goes in, whether it's us or a star or a computer or anything, the exact same thing happens to it in the end, unfortunately. So nobody actually go to a black hole, please. You won't make it out. Alrighty. Okay, we're good, I think. Amazing. Well, thank you guys so much.